Hi everyone, and welcome to the fifth video of the Peer Club R series. Today I will give you a short introduction on loops and the functions in R. Just to prepare you, the first part of this video will focus very much on actual programming in R, while in the second part I will mention some of the statistics that we've already heard before, especially in the last workshop that was organized by Kira, but I'm going to repeat some of it as it is relevant for the function that we're going to be developing. This time, you can just lay back and watch this video. You do not need even to open R because all of the coding will be done in the following video. Well, this video is just an introduction in preparing you to what is going to come in the next video. So what are loops? Loops, per definition, are special constructs allowing for the repetition of instructions or automation of multi-step processes. This basically means that if you write a loop, you're saving yourself a lot of copy pasting, a lot of typing, and you can basically just repeat a lot of steps just in one piece and execute everything at once and even leave the computer and just let it run. So it's definitely very, very helpful. And I would call myself a huge fan of loops. And I will hopefully convince you why you should use these as well. There are a few different kinds of loops and statements that can be combined with your loops to make them run properly. I would say that the most common and mostly used loops are the for loops, where the number of executions is controlled by a counter or an index, or the so-called running index, which is also going to be the term that I'll be using throughout the two videos. Then there are the while and repeat loops, where the execution is controlled by a logical condition. And then there are if-else or if-else statements, which are not actually loops, but are often combined with loops, and they're controlled by a logical condition. So when and why should you use loops? As I already mentioned, using loops is helping you to avoid copy pasting chunks of your code, which makes your entire script much shorter. And secondly, it is easier to see important parts of your code, which are, for example, parts that are different from each other rather than operations or processes that are the same and therefore are repeated throughout your code, making it just very messy. It is also easier to make changes that affect these repeated processes. So it means that you can just change it once in your loop and it will automatically execute this new change for all the steps within the loop or for all the arguments that you have added to the loop. Also, you can this way automate your processes so that there is no further need for your input and you can just let it run on their own. So you can basically start the loop, leave the computer if you know it's working, and you can come hours later and everything's going to be done. So using the loop just allows you to run long processes where you as the user do not even have to be present, which I think sometimes is very helpful, especially if you're running very, very long loops that might take several hours. And the most important thing, and this is how I feel about it, is that you are the one who controls the loop. So compared to all the packages or everything else that you might be using, here you're writing the loop yourself. You're writing also maybe the functions yourself that you are building into your loop. And by that, you have the entire control of what is happening in the loop. I will shortly introduce the for loop. So the general construct of the for loop is basically this. So we have this first part that is just named for, and then we have this argument here, so this input, which in this case is just I in a sequence. And I in this case is the counter or the running index. And then we have the curly braces here, so at the beginning and at the end, right? And in between, we have the actual body of the loop, which is the code aside. So this is where the actual process is happening. So it's within those curly braces. To make it easier to understand how a for loop works, we can look at a flow chart. So start with each item in a sequence. So this is for each running index that can either specify just a number, or it can also specify an index within, let's say, a data frame or a vector that should be evaluated. The loop is first checking if the last item is already reached. If the answer is no, then the body of the loop is executed and your process is running. And then the entire loop is repeated again. So it goes back to the part where it's checking again if the last item is reached. And if the answer is again no, it's executing the body of the loop and just repeating this whole process again and again. If the answer is yes, so once the last item has been reached, you're exiting the loop. Here are a few examples how to initiate your loop and what you can actually use as the running index or the counter for your for loop. So for example, you could have the item I or the number I in a sequence of numbers going from 1 to 1,000. So it's taking all integers from 1 to 1,000 here. Or you can also specify a sequence where you have a specific step. This is a sequence that goes from 0 to 100, but in steps of 10. So it's going to take numbers 0, 10, 20, and so on until 100. Then you can also, for example, have an index of rows. So you could just start with the number 1 and they go until the end of a data frame. So for example, here the F stands for the data frame and N row stands for the number of rows. So you're basically running this loop for each row of your data frame individually. Or you can also do the same for a vector. So you start with the first element of the vector and then you run the loop until you reach the last element of the vector. So that's why we're taking the length of the vector. Or you can, for example, just have items within this vector. So for example, either numbers or strings. And then this running index I, instead of just starting at 1 or 0 and going to a certain number, is basically just going to take each element of your vector. So if your vector is apple, pear, plum, your I will be apple, pear, plum, and will run for these items. Then there is the while loop. The general construct of the while loop is that it starts with a test expression and then again has the code within the loop where the actual process is happening. In the flow chart, we see that you first enter the while loop and then you're getting to this test expression. And if the test expression is true, then the body of the loop is executed and the entire loop is repeated. If, however, the text expression is false, then you're exiting the loop. For example, you can write a loop like this. This loop here is taking the running index I, and as long as the running index I is smaller than 10, it's going to run this inner part of the loop. So every time I is smaller than 10, you will start, for example, you can define I as 1 before you enter this loop. So I will be 1, and once you enter the loop, you will basically add 1 to your I and assign it again to I. So basically just overwrite your I. So I will get 2, and then using the function cat, you can just print the number I into your console. So it will just print the number 2. And then this is going to be repeated until I gets 10, and this will then stop the loop. If and else statements can be combined with while and for loops and are testing a condition. So for example, if you want to find out if a given number is odd or even, you could write the following. You can start with a for loop. So this is going to be our most outer loop here. And we are going to use a running index n, which is going to be between 1 and 10. So all integers between 1 and 10. And then we can write an if loop. And this loop is checking if the remainder of the division of n by 2 equals 0. And if this is the case, then the body of the function is going to be executed. And the sentence number and then the actual number that is currently evaluated is even will be printed. So in this case, for example, the number 2 divided by 2 will not have a remainder. So it's just going to be equal to 0. So this expression here within the if loop is going to be true. And then this body is going to be executed. And you're going to get the output saying number 2 is even. Just as a small note, this backslash with an n here just means enter. So every time a line is written, R will just make a new line. And by this, you can separate your text and make the entire text that's going to be produced in the loop just appear always in the next line. If, however, this statement here is not true, which, for example, obviously is going to happen whenever we start with 1, because 1 divided by 2 is going to have a remainder equal to 1, which is not equal to 0. Then you can just here either take another loop, which is going to be another if loop, but then with the exact opposite condition here, or you can just use the else loop, which you can basically just add after the if loop directly, so after the curly braces. And then here, we just have the sentence number, and then the number is odd. So if the number divided by 2 has a remainder of 0, the sentence number is even is going to appear. And if the number divided by 2 has a remainder that is 1, then the sentence number and then the number is odd is going to be printed to your console. So if we now execute this entire for loop, then this is going to be the output that we're going to get, and so on. One thing that I haven't mentioned before are the break and next statements that can also be combined with your loops. So for example, if you have NAs, so non-available values in your data set, you can, for example, skip them while you're running a loop. And the way you can do that is either by using the break here. So we start here with a for loop that runs for the running index m, that runs from 1 until the last row of your data frame. And then every time it's checking if the element at the position m within the column x here is an NA or not. So if this is an NA, then the loop will break. In other words, the loop will stop entirely. If, however, you want the loop to just continue and basically skip every element that is an NA, but continue with the very next element or with the process that comes after this step here, then you can just use next. So whenever this statement here is true, then your loop will not be executed here. So the if loop is not executed, but the entire loop is just continued with the very next step if there is any. If there is no step, then it's just going back into the outer for loop until you reach the last row of your data frame. If you do not like loop, and you might have your reasons, there are some alternatives that you might want to use. For example, in base R, there are functions from the apply family that can be used. And then in the per package, there are functions from the map family. And there is the special case where you might want to use the for loops, often in combination with if and else loops for your data organization. So for example, you want to reorganize or rearrange your data. You definitely can do that if you feel comfortable with that and know how to do it. But you also might just use the functions from the packages dplyr and tidyr, which offer a range of functions that can easily do the work that you want. And if you're interested in that, you can also watch the video for some of the details. Personally, I'm mostly using for loops whenever I have a really cool idea about something that I could automatize or something for which I know might take long because I'm testing, let's say, many different parameters or similar, then I'm definitely going to go for loops. However, just keep in mind that for loops can get very slow, especially because the way they work is that they're really checking every single element. So some of the other functions from other packages here might be more helpful. But don't forget, as already mentioned, you're the one who controls the loop. So if you feel more comfortable by just writing a loop because you actually know what this loop is doing, because you wrote it and you checked every step of it, then just go with that. Now we can go to functions. So functions obviously are the core of coding. So everything that we do in R, or at least most of it, is just using functions. There are built-in functions, which you are probably already aware of. So these are all the functions that come with the packages, are also part of the base R. But there are also the user-defined functions. So these are the functions that you can write yourself and then use them within your scripts. There are also specific functions that are defined by the object class. So for example, the functions plot and print. And you might have noticed that if you've been working with R for a while now, that you can use plot and print on very different classes, and it will give you a totally different output sometimes. Just as a small exercise for today, try the following in R. Write the code methods and then plot in inverted commas, and then methods and print in inverted commas, and then just see what you get as an output for both of these lines of code. So back to the functions. A general construct of a function is this here. So you can start with just writing function and then assigning it to a name of choice. You can basically write whatever. You might want to check if the name is already taken so that you do not overwrite any of the functions that belong to either base R or any of the packages. And after the word function, you can then use the parenthesis and specify the input of the function. So these are all the arguments and parameters that you are providing to the function that are then afterwards used within the function. And then again, you have here the curly braces at the beginning and at the very end. And inside of this, you have the body of the function, which is the code inside of the function and the actual process. And then you can use the function return here to return the output of this function and, for example, assign it to an object. So this is then the output, which can be values, it can be vectors, it can be lists, it can even be plots or entire data frames, or basically even just a mixture of everything. The way you use this is that you just type in function name and then you add all the input that is necessary. You will see that sometimes the input is already predefined. So there are things like print equals true, which means every time you execute this function, you do not even have to add this argument. The function has this setting as a default, so it will always print something, okay? And you can even define these arguments yourself. So you can start a function, you can add some of the arguments that are not defined at all, and you can also add some of the arguments that you're going to predefine, but they can still be changed. They're just going to basically be there as a default setting. If you want to know more about the functions, you can check the function components. These are the list of arguments which can be assessed with the function formals. Then the code inside of the function, in this case without the comments if you're using the function body. And using the function environment will usually give you either the global environment as the output or the name of the package where this function comes from. You can also use the function getAnywhere, which will show you all of the above. There is also the function attributes, and here you can use the function name and then just add this word here, so this string, which stands for source reference, and this will show you the code inside the function the same way as the function body does it, but it will also include all the comments. And if you're, for example, writing a function and you save it as an R script, and it's outside of the actual script that you're using for work currently, you can use the function source and just type in the name of the R script where you saved your function and then call your function from this R script. As a small exercise for this part, you can try these functions here. So for example, formals, body, environment, and then getAnywhere for the function gmUpline from the package ggplot2. So now to the last part, and this is going to be a little bit more about statistics today. The idea of this video is to give you a short introduction on a function that we are going to develop in the next video, where we are going to do all the coding. And I named this function ggNorm. So the purpose of the function is basically to check the normal distribution of the data. And while it's doing so, give you plots as an output that are produced in ggplot. So this is why it's called ggNorm. So the background to this, and here comes the statistics today, certain statistical tests assume normal distribution of the data. And you might have already heard that, so I'm really sorry if this is going to be too much of repetition. So what are the properties of a normal distribution? So here there are different opinions, but I'm just going to stick to 3 rules. First rule is that the mean and median are equal, or at least within 10% difference. Second rule is that the mean is larger than the variance. Here, however, I have to mention that I have not really found a source that is actually confirming this. And just from experience, this also doesn't always work. So just have it in mind, but honestly, do not really stick to it too much. And the third rule is that at least 2/3 of the data lie within mean plus standard deviation. There is also the empirical rule, which says that approximately 68% of the data lies within mean plus 1 standard deviation. 95% of the data lies within mean plus 2 standard deviations, and 99.7% of the data lies within mean plus minus 3 standard deviations. So let's look at this graphically. Here I'm showing a typical normal distribution of the data. So this is the probability curve plotted against the actual measured variable. And this measured variable here was chosen in a way that it has a mean value of 6 and a standard deviation of 1. Okay, so the black vertical line here is going through the mean, and this blue line here is the probability function. Here I'm just showing the code that I used to produce this data. So you can use the function rnorm to basically create a data set that has, in this case, 1,000 elements, a mean of 6, and a standard deviation of 1. And then you can use this created object here within the function dnorm, and again, just add the mean and the standard deviation here, and this should give you this curve. So if we now look again at this curve, we see that it's unimodal, so it has this one peak. Then we see that it's symmetric, which in this case means that the mean equals the median equals the mode. And we also see that it's asymptotic. So these are also 3 other rules or properties for a normal distribution. Now, if we look at the empirical rule, what it actually says is the following. So this here is the area that is exactly between the mean, which is here 6, and then -1 standard deviation and +1 standard deviation. And we see that on each side of the mean, the proportion of the data that is within this area is 34.13%, which together makes up 68%. This is then the proportion of data that is within mean -2 standard deviations and mean +2 standard deviations. And we see here that on both sides, we have another 13.59%. And all together, so all these 4 areas here add up to 95% of the data that is within these margins. And then if you look at the mean -3 standard deviations and mean +3 standard deviations, we get another 2.14% on each side, and everything together then sums up to 99.73%. What we also sometimes use to check for the normal distribution are the QQ plots, so the quantile plot. And here we are comparing the sample quantiles, so the quantiles from your actual data set that you have, from your measured variable, against theoretical quantiles, which in this case come from a normal distribution. And if these are the same, then most of your data is going to be on this line here. And we see here the data that we produced is actually very normally distributed and is nicely distributed on this line here. Okay, now back to the actual function that we want to develop. This is the output of the function. So we see these 3 plots here. The bigger plot here on the left is a histogram with a density curve, the mean, and the standard deviation. So as a small exercise for you, you could think until the next video, which are the elements you have to consider here, that you have to calculate, that you have to include as the input for the function, and which functions within your user-defined function you would use to create a plot like this. So we see here, we have a line, the green one here, that is representing the actual normal distribution. We have the dark blue line here that is representing the actual distribution of your data. Then we have the histogram here in the background, the red line, which is the mean, and then we have the dashed lines here that are representing mean -1 and +1 standard deviation, and then the dotted lines here that are representing mean -2 and +2 standard deviations. Also, we have a title here, which actually says which variable here is plotted and if there is a certain condition. So for example, here we are looking at the bill length of the Adelie penguins, which are females. Then here on the bottom on the left, we have a box plot. And this box plot is helping to see if the mean and the median are similar to each other. So that's why this box plot is exactly placed below the histogram, and it's in the same range as the histogram itself. And we can also plot the raw data here to once again see the actual distribution of the data. And if you use transparency here, you can also see all the points and you can see where are the places where these overlap, meaning that, for example, here you can see that some of the points are much darker, which means that there are many points overlapping. And also you can see here that we have this higher bar, and the same happens here in the middle where we have these higher bars. Again, you can see here that we have the variable name here at the bottom of the box plot. And then as the third element of this big plot is the QQ plot that I just mentioned. Again, here we have the title and we have the actual data in the line. And the last output from the function is a table with summary statistics. So you could also have a think how you would calculate all of these. So we have the p-value here from the Shapiro's test, the median and the mean, the variance, then one standard deviation, two standard deviations, and then the percentage of the data that lies within the mean plus and minus 1 and 2 standard deviations given in percent. So these are the four elements of the output of this function that we are going to create. So as I said, until the next video, you might just have a think, what is the input that we need for this function? What are the small things that we have to control for? What are the other functions or other packages that we might use, and so on. So thanks for sticking with me. And yeah, see you at the next video. Hi, everyone, and welcome to the next video within the Peer Club R series. Today, I'll be talking about loops and do some partly live coding, partly just showing the code that I prepared. And I would say that loops are by far my favorite topic in R, just because I really love them. I use them a lot. I would say that most of my really cool scripts contain at least one, if not even 10 loops. And there was even a running gag whenever I was doing my PhD that basically, so almost every question that someone would ask about R, I would just be like, yeah, you could just write a loop. And I think that this is still the case nowadays. I am aware that there are alternatives, such as many functions that are in dplyr and tidyr, which I already mentioned, can be used to reorganize your data, or, for example, do many things at once, like run multiple models. That is then usually in combination with the per package that has many different functions within the map family that can be used instead of the for loops, for example. And these probably work pretty fine, I would say, and I'm definitely aware that these are there. I'm aware that these are maybe even faster than the loops that I'll be showing today, or the loops that you would usually use. However, as already mentioned a few times, I find that a loop is very beneficial because you have the control over it. You can add all the small bits and pieces that you want to have. If you want to calculate something specific, you want to make a plot as well, you want to have a specific label, you want to just like add lots of bits and pieces into it, then the for loop, or a combination of for loops and while loops together with if and else statements, is just a really great tool to get you where you want to get in, well, probably a short period of time, at least compared to where you would get if you would have to do everything manually, or if you would just do copy pasting. But yeah, it's just a lot of freedom that you have, but also a lot of control that you have. And also it's really great if you just like need something for your brain. If you just need to like think a little bit deeper about things, just have all of these processes in your head. It's really just fun. So I hope you understand why I like them. And I'll try to just give a short introduction, I hope, on some basics, and then hopefully go to something a little bit more complicated so that we have kind of a basis that we can all work with. So you're going to start with some very simple loops that are already prepared here. I showed them in some of my previous workshops, which was on data manipulation in R. And it was just a really, really small part of this workshop. So I'm just going to repeat that because the examples are really useful and easy, I would say, and then maybe go a bit further and put a little bit more details into it. Okay, so a really, really simple loop. Let's just imagine you are simulating flipping a coin 1,000 times, and you want to count the heads, and then just calculate what is the proportion of heads in these 1,000 times that you flipped a coin. Okay, so we can do this with and without a loop. So I'm definitely going to demonstrate both, and we can even see which of these methods is faster. So first of all, you have to kind of define a coin, okay? We're just going to call it X, nothing special. And obviously a coin has two sides. And in this case, we're just going to give it a 0 and 1. In this case, 0 is going to be for the tail and 1 is going to be for the head because we're interested in the head. Okay. And then we can run this. And this is just a simple vector. C here stands for combine, as I just learned recently. And now we have this object called X here that has two observations, which is 0 and 1. Okay. And then, as I said, we want to do this 1,000 times. So we can either just use the number 1,000 afterwards in the command sample, which is then here in line 31, or you can define a number of times that you want to flip the coin and use this object afterwards. Okay, so we're just going to define n as the number of times you want to flip the coin, and it should be 1,000. And then what we're going to do is that we're going to use the function sample, and this function takes basically a set of data. Okay, in this case, this is our coin that has the data 0 and 1. Then it takes the number of times you want to sample something. And then you want to tell it if you want each of these sampled items to be replaced or not. Obviously, because you're working with an object or a data set, let's say, that is smaller than the times you want to basically draw a sample from it, then you definitely have to specify replace equals true. Okay, so we're going to do this here. We are going to add here the X, which is our coin, then the number of times we want to flip it, and just set replace equals true. And we're going to save this sample in an object. Okay, because if you run this sample a few times, really just this part here, it will always give you a different output. Okay, but we want to save this output and we want to use it for something else afterwards. And we're just going to call this output simulation. So we run this now. We don't see anything in the console because we just assigned something to an object. So there is currently no output, but we see in the environment that we have a new object here called simulation, which has in total 1,000 observations. Okay, so we can now look into this object here by just calling it once again. And we see here it's just a lot of zeros and ones. And now what we want to calculate, I think I should just quickly change these here. Okay, cool. So by the way, this is a small thing that I'm just going to show. If you just want to switch the positions of lines, or if you just want to move some lines up or down, you can basically put your cursor somewhere in the line and then press Alt and then use your arrows to basically move this line up or down. We're going to move it up and we're going to move it down. Okay, just a small tip. You can also mark multiple lines, press Alt, and then move them up and down. This indeed comes handy sometimes. Okay, so what we want to have now is basically the number of heads. And we know that we defined head as 1. So we can basically just calculate the sum of all these ones that are in our object simulation. And if we do that, we get the number of 494. If you're doing this at home, you might get a different number. This is basically because when you use sample, you always get a different probability of what you're going to get out. It's usually very similar, so it's going to be kind of in a specific range, but just be aware that it's going to be a different number maybe, okay? And now we want to have the proportion, so we're going to just divide the simulation by the end of times that we flip the coin. You can also do it in a different way. I'm going to show it in a second. And we're going to multiply this by 100 to get the proportion in percent. And we get the 49.4%. What you can also do, again, is to use sum of the simulation and then divide this by the length of this object. Okay, we know that this object has the 1,000 elements. So you can just use the length of simulation here. And then again, multiply this by 100 to get the percentage, and it's going to give you the exactly same output. Okay, we can do it in another way. For example, here, instead of just using 1 and 0, we're going to call this head and tail. And we're going to put these two strings again in a vector, and we're going to assign this vector to the object y. And then we're going to run another simulation. So again, we just use the function sample here, then y, and then n for the times you want to flip the coin, replace equals true. And we run this, and we see here that we have the object simulation in our environment. And here it's of the data type character because it has these strings. And we can look into it. So we see it's lots of heads and tails. And if you now want to get the number of heads inside, there's a really cool way to do it. So basically what you do is that you again take the sum, but you're only interested in heads. So you're only interested in the elements of the object simulation dot two that are equal to head. Okay. So if this comparison is true, it's going to give you a 1 because true is the same as 1. And if this comparison is not true, the output is going to be 0. Okay. So only when the simulation.2 element equals head, you're going to get to 1, and then you're going to just sum all of these together. And if we do that, we see here that we have 490 heads in this second simulation, and this is equal to 49% in total. Okay, so we've done this, and now we can try to do the same using a loop. I'm going to try to explain this in a really easy way. I'm just going to go first to the loop. Let's just look at this very first line here. I'm going to skip this for a moment. Okay, so in this very first line here, we're defining a for loop. That's why it's called for here. If you want to write a for loop, and I'm just going to show it here in the console, and you're not sure about the structure, there are snippets that I mentioned at some point. This snippet looks like this. You just type in for example, and you already see here that if you just don't do anything, right, it just shows you this very first option, which is from snippets. And if you just click on that, then you get exactly the structure that you need. Okay, so you just have to press enter, and you already get this this entire construct that you need to basically build your for loop. Okay, so just a small thing on the side. I'm going to remove this here. Okay, so I want this loop to run from 1 to 1000. So we have this running index here that I'm going to call I, which can stand for item, or as I said, I call it running index usually, and that's why I mostly use the letter I here. And it should be from 1 to 1000. Okay, so 1 to 1000 can be written like this. I'm just going to quickly demonstrate this in the console. So these are basically just the integers between 1 and 1000. Okay, so I want to repeat this 1000 times, going from 1 to 1000. And what I want to do first, and this now is the part of the loop in here, I'm just going to subdivide these a little bit better so that you see what's happening. In the very first part here, I want again basically to just flip the coin once. Okay, so we're sampling here from head and tail. We could also just write the Y here. And then we're doing it only once. I have not added replace equals true or false, because in this case, it doesn't really matter. We are only drawing one sample out of head and tail, first of all. And second of all, the replace equals false is the default in this case. So it's already in the function. And you do not have to specify it again. You should only specify it if you have to change it to true, for example. But in this case, as I said, it doesn't really matter for us, so we can just leave it like this. And we just spare some time and a few letters of code, okay? So we save this as a sample and assign it to the object A. And then here in the next part, we use the if statement. And this statement is controlled by a logical condition. So our logical condition here is that A has to equal to head. So we know here that we are flipping the coin only once. So A can only be either head or tail. And if A equals head, then this inner part of the if statement, so the body here, will be executed. And this is now where the letter M, or the object M, comes into play. We see here in line 48 that I'm defining M as 0. So this is basically just my starting point. Okay, so I have an object that is currently just 0, but whenever I find a head here in my sample, so whenever I flip the coin and the result is head, I'm just going to overwrite this object M. So I'm going to add 1 to the object and just assign it again to the same object. And this way, I'm just going to increase M each time that I flip a coin and I get head. Okay, so at the end, basically, M should give us exactly the number of heads that we got as a result of flipping the coin 1000 times. Okay, sorry if this was confusing. we're first going to run this. So m equals 0, okay? And the only thing you have to do here, and if you have one of the newest versions of R in RStudio, then this should work if you just put your cursor somewhere in the first line. I would usually just put it somewhere either in the word for or maybe just before that. If you put the cursor here and if you just press Control and Enter, or on Mac it should be Command and Enter, then it's going to run the entire loop. And we see here that there is no output. So basically it's just running the loop. But if we look into the environment, we already see that m here equals 505. And we can also do this here. So we can go to line 60 and run the line 60. And we see again that m equals 505. So 505 times out of 1,000, we flipped a coin and the result of flipping was head. Okay, so that's a way how you can use the loop. And this again is a combination of having an if statement as well, having a run-in index, which in this case is I, and then having an object that we are increasing throughout the loop depending on the condition. Okay. There is also another way, let's say similar, more or less. So we first define an object that is just called my flips. Okay. I think it should be my flippings, but it doesn't really matter. Let's just forget about that. And I'm just making a vector out of it. But this vector is entirely empty. So there is nothing inside. Okay. I'm just calling it my flips and I'm running this. And if we now look into the environment, we see here my flips is just null. Okay. If you want, you can also do the same. You could also just write my flips null. And I think that should work as well. Okay. Good. Then what we do, again, we just write a really, really short for loop here. So we start again with this first line that says for I in 1 to 1,000. Okay. And then what we do is that we again have a sample here. And we're choosing again between head and tail only once. But what we're doing is that now we are saving the output of this function into my flips object at the position I. So this means that if we start with 1, and this is, by the way, important here that you always start with 1, obviously, it makes the most sense, basically. It means that very first time when we flip the coin, the result of the flipping is going to be saved as the very first element of this object, okay? I can just quickly show how this would work. So this is also a way how you can check if your loop is working properly. We're going to define I outside of the loop. We're just going to say I equals 1. So we just do it quickly in the console, okay? And we check I equals 1. And then without running the loop, we just run this part here. So everything is here that we need. We already have defined my flips. We have defined I, and now we just use this function here and then assign either head or tail to the very first element of this object here. And if we do that, and if we look into flips, we see here that flips now has head inside, okay? And that's at the very first position. We can also check that. And we see here, if we just type my flips and then the square brackets and then 1 or I, it doesn't really matter in this case, we get head. Okay, I'm kind of demonstrate this again. So this is with I, and it's also head. So now we are going to increase I. So I is now going to be 2, obviously. And if we now run this and go to my flips here and just run this one line again, so just the line 67, then we see here that my flips now has 2 elements. The first element is head, and then the second element is tail. Okay, so we have 2 elements now. And we can do this a few more times as well. But obviously, we're going to just do it in the loop. You can, and I would definitely recommend that, first again run the line 64, just to make sure that my flips object is empty. So we do that. So it's again equal to null. And then you just run the loop. Okay. And now we see that my flips also has 1,000 observations. Okay. And I can also show how this looks like. So again, it's just lots of tails and heads. And again, we can use the sum here to just check the number of heads that we flipped. And we can use this again and then divide this by the length of my flips here and take it times 100 to get the proportion. So the proportion is 51.7%. Okay. So we're now done with this. So this is basically really simple to do. But what I already mentioned is that sometimes these loops are taking a bit longer than something else might take. So it might be that the for loop is taking longer than, for example, the map function from the per package. You can definitely play with that and try it out. I'm just going to quickly show you how you would check that. Okay. So I'm just going to take two examples. I'm going to go up again here where we defined x and n, and then we do these simulations here. And I'm just going to take, let's say, this part here. So just the part that gives me the actual number of how many times flipping a coin resulted in head. Okay. And what we're going to do here, I'm going to assign time to an object. And the way you do this is that you just type sys_time, okay, and then the parentheses, and that will save the time into the object start. Okay, I can demonstrate this quickly. And if we now look at the start, we see here that we have the date and then the time. Okay, and then at the end of the code that you want to run, you can also just do this again. So you just say here end, and then again the time. Okay, and then we want to know the difference in time. So we're just going to call this diff, and this difference is just basically the end minus the start. And I'm putting this entire thing into parentheses, because if we do that, then we're automatically going to get the value written in the console. If we would just exclude the parentheses, and I'm just going to do this quickly. If we exclude the parentheses, we have assigned something to diff. If, however, we put everything together into the parentheses, okay, and then just run this, then we are also automatically going to get the output here, which says that the time difference was 46 seconds in this case. Okay, so if you now want to know what is actually the time that you need to run this part here, the best way is just to mark everything together, okay, and then just press Control and Enter. And we see here that this was super fast, so 0.03 seconds, okay. And now we can do the same in here for, let's say, this part. Again, we're just going to add the start here, okay, and then we're going to add the n here, and I'm just going to leave m here as well, because in the part before we also show the entire object, so I'm just going to account for that as well. And again, here, the difference is going to be end minus start. Obviously, you can also use different names here. You can also just say end 2 and start 2 and difference 2 if you want to keep all of these objects together. But honestly, it really doesn't matter. We just want to have a time difference here. So you can just combine all of this, okay? And again, just Control and Enter. And we see here, for example, it seems like the for loop was quicker, okay? It might be that us, for example, defining x and n before just takes a little bit longer than basically just doing the sample here, and so on and so on. There are different factors that can play a role, but I just wanted to demonstrate how you would do this with time. Obviously, these are just examples, so we just run one part of the code once and the other part of the code once. If you would run these maybe 100 times, 1,000 times, and then always just calculate the time, you can also do this in a loop, obviously, and then just take the mean of the time, then you might see a proper difference here, okay? I mean, this is very close, so we can't really tell which one of these is faster. This obviously only plays a role if you're running really long scripts, where you have long for loops, where you can look for specific parts of the code where you might just use something else rather than a loop, and then just basically decrease the time that your script needs to run, okay? As I said, this is a bit more advanced, and it's for people who work with much larger scripts. For us, it doesn't really matter at this time point, but at least I've shown you how you would check which of these takes longer, and you just have to account for different things that you do. So are you showing the object? Are you not showing the object? Are you just assigning something to it and keeping it basically just in the environment, and so on? Okay, and there was one last bit that I wanted to show. So here, for example, we're going to do just one more thing more than before. So here we're going to use my count as an empty object first. And then we're going to run the loop again for 1 to 1,000. And this time we're using the running index j. It really doesn't matter how this is called. You can call it whatever you want. You can call it banana, you can call it apple, you can call it j, a, p, it doesn't really matter. Just don't call it c, because c is a vector and I just don't really like using that, or maybe also do not call it f. But yeah, every other letter or word or whatsoever, you can totally go with that. Okay, it doesn't really matter as long as you know how to afterwards use it also within your function. Okay, so what we're doing here, we're just doing the same as we did before, but now we are flipping the coin 1,000 times. We're saving each of these samples into the object mySample, and then we're calculating the sum of all occasions where sample equals head. So basically just counting the number of heads and saving this number into our object myCount. Okay, so we're not saving the actual flips into the myCount object. We are already saving the number of heads that we get when we flip the coin 1,000 times. So we flip the coin 1,000 times, we save the number of heads into the myCount object, and then we flip the coin another 1,000 times. And so we repeat these 1,000 flippings in total 1,000 times again. Okay, and we're going to end up with a myCount object that is going to have 1,000 elements again, which are all going to contain the number of heads that we got when flipping the coin 1,000 times. Okay, so if we run this now and then just check my count, we see here we have lots of numbers inside. They're all somewhere around 500, obviously. And if you calculate the mean is almost 500. So this is also showing you that obviously all of these theories of probability, they totally work. It's really just the number of the flippings, or like just the number of repetitions. In other words, your sample size that matters here. So now we've repeated the same process 1,000 times and have each time extracted the number of the coins that were head, and we get the mean here, and the mean is 500. And this is exactly what we expected. Okay, so this is for this first part, just showing some really, really simple examples. I'm going to show another example that I also mentioned in my slides. Just making a new section here, odd versus even. So I showed in the slides that we can also write a for loop that is just telling us if a number is odd or even. Okay, so it's just going to write a sentence saying number something something is even, okay, or number something something is odd. So what we can use here for this is this syntax here, which basically is giving you the reminder of a division. So if we just run 5 divided by 2, this is going to give us the remainder, which in this case equals 1. Okay, if we do this, for example, for the number 6, obviously the remainder is going to be 0. And this is exactly the difference that we can use to decide if a number is odd or even. So if the remainder is 1, the number is odd. And if the remainder is 0, the number is even. And now we can put all of this in a for loop. So we're just going to do it for numbers from 1 to 20, let's say. So let's take here k in 1 to 20. Okay. And you always need the curly brackets here. So you first have for, and then in the parentheses, you have your running index or your item, and then some kind of a sequence or a vector or whatever you want to use. And you have the curly brackets. And then here, always just make a little bit space. And then here we are going to use again the if statement. So we're going to check here if k divided by 2 equals 0. And if this is the case, then this number is even. Okay, so this is now the condition. This is the first part of the if statement. And this is now where the body comes in. So we just want R to print the sentence number k, in this case, is even. And you can either use print or cat. I usually use cat here. So just going to say here number, and then outside of the inverted commas, we're going to write the k here. Okay, so comma, and then k, and then again a comma, and then here is even. Okay, so this is a sentence that is going to appear in the console if the number that we're currently looking at, so the number that you're currently evaluating, divided by 2 has a remainder of 0. Okay? And then if this is not the case, so we're just looking at the opposite condition. In this case, we can only have either 0 or 1. Okay? Then you can use else here. So this is just the opposite. And if this is the case, you do not even have to add a condition here. R will know that the condition here is just the exact opposite of what you inserted here in the if statement. So it's just enough to put else here, and it should be after the curly brackets. Okay. Then you again open the curly brackets. It's now referred to the else statement. And then here we add the same sentence. You can just copy paste it, but here obviously it's going to be odd. And then you can basically just run this. So we have everything that we need. We have the running index, which is from 1 to 20, and we are dividing this number by 2. And if we get the remainder of 0, then the number is even. And if we get the remainder of 1, then the number is odd. One last thing, and this is something that you might forget when you do it the first time, because you're going to get all of these lines printed into your console, you also need to tell R to go to the next line, which R will not do if you don't tell it to do it. So what you can use here in both cases is just that you add a backslash and N. Backslash N means enter. In other words, new line. Okay, and we're ready now. So there are no red crosses on this side. So everything is cool. All the brackets, parentheses, and curly braces, everything is there. I'm just going to remove this small part here. Okay, so now we can just run this and voila. Looks beautiful. We have everything that we wanted. It's basically just putting the sentences in the console and it all looks correct. So number 1 is odd, number 2 is even, and so on and so on. Super, super cool, at least in my opinion. Okay, so this was odd versus even. Then just for fun, because it's, at least for me, very entertaining to do this, it was just recently that I wrote probably the funniest and the shortest loop ever, which basically fits into one line. And I just want to show it here. I'm just going to call it funny loop because I love it so much. I know you're probably going to think I'm totally weird, and I am. Okay, so this is a really funny one. I'm just going to write it first. So I'm going to run this 1,000 times. Well, no, that's too much. Let's just run it 100 times. And we're just going to call this D. So D in 1 to 100. And then I'm going to add the curly braces here. Okay. And then first, I'm going to say to R that it should use the if statement. And if D equals 1, okay. And now we again need the curly braces here. Okay. Then I want R to print the word loop. Okay. So that's everything that we have in this if statement. So this part here is the if statement. And then if this is not the case, so the only other option is that D does not equal 1. Okay, so it's going to be for all these from 2 to 100. So I'm just going to write else and again add the curly braces here. And now I want R to type in a loop. And just see here that I added a small space. Okay. And I'm just going to add a space here just to make it a little bit more visible. So this now is your else statement. And this is everything. So this is the for loop. This is one line of code. And this is the output. I don't know if you expected more or if you expected less. I love this. It's just loop and a loop and a loop and a loop and a loop. And it's just funny and it's cool. And it's just showing again that you can, first of all, do nerdy crazy stuff. Second of all, that you can also put all of these things into one line of code. Okay, just on the side. And then I'm going to do something that many of you might even find very helpful. Let's see how we're going to call this. For loop for folders. Okay, many F's here. Good. So this is something that I started using at some point when I decided that it would be good to maybe have some of my data sets that I was working with subdivided into different parts and then saved into different folders. We're going to do this first. So we're going to have a data set that is going to have some variable that is categorical in some way, and that is just grouping your data together into a specific group. And we're going to use these groups basically to subdivide these data sets into individual ones. And then we're just going to save these data sets as CSV files into a folder. Okay. But these folders are all going to be created within a for loop. And then in the next part, we're going to do the quite opposite. We're going to open each of these folders, take each of these files out, and combine these files together. Okay. I'm not sure if you can do something like this in Tidyverse, or probably you can kind of like maybe do it with map or something. I'm not sure. But this, I think, is a really easy way to do it. And it first of all also shows you cool things like creating a folder. And thanks again to Klena, who was the first one who ever mentioned this. So this is a really, really cool idea that, as I said, at some point I started using. And especially this opposite part where you basically have your folders and you're getting the name of the folders and you're going into each folder, getting the file out, and basically putting everything together into a big data frame. This, I think, is something that many people would do if they are working with a specific software that is always giving you this separate files, so these individual files. Sometimes these individual files are just saved in one folder. Sometimes they're saved in different folders. So if any of you has ever worked with, let's say, gas chromatography, a GC, for example, the one that I worked with, I think from Agilent Technologies or something, would always measure one sample and put all files that refer to this one sample into one simple folder. And this folder would then have the name of the sample. And these files, however, will all have, for example, the same names. So it's always going to be, I don't know, report one as a CSV, report one as a PDF, report one as text file whatsoever. But each of these samples had a different folder. So if you wanted to get all these together into a folder and just like extract some data of all of these files, the best thing, honestly, was just to use a for loop. And I even wrote a script one day for that, and it was super helpful because all the colleagues loved it because it saved you so much time. It saves you the time to go into each of these folders, open each folder, open the CSV file, copy paste the data into a new file, and so on and so on. So all of these things you can do with a loop, and you can do it with R. Okay, cool. Oh, this is so exciting. So first, we're going to create a very simple, totally boring data set, which we're just going to call df. Super boring. Okay, and here, what you're going to do, we're just going to have, let's say, letters. Okay, and let me just see something. So letters is an object in R that basically just has all the letters of the English alphabet. Okay, so I'm just going to repeat these letters 5 times. Nothing special. Okay, and I'm going to do a data frame out of this, and I'm just going to call this group. Okay, so my first column in this data frame is going to be called group, and it's just going to have these letters. And I'm just going to call it here each 5. Okay, so a difference, and I'm just going to try to show it here, is if you want, for example, to repeat the letters A and B 5 times, you can do it in 2 ways. You can either do it like this, so that would be the first option, and then what you're going to get is AB, 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 AB. Okay. However, if you want to have A 5 times and then B 5 times, then you have to add each here, and then it gives you this. Okay. So this is what I want to have. I want to have 5 times letter A, 5 times letter B, and so on and so on. And let's just check how long this is. I obviously know how many letters are in the alphabet, but just to show this. So it's 26 letters. Whew, that's exactly what I expected. And 26 times 5 is 130. Okay, so we need 130 numbers that we're going to put into the other column here. So we're going to call this column just volume. Okay, and we're going to add 130 numbers aside. I do not want to just write 1 to 130, so we're just going to have sample here. We're going to sample numbers from 1 to 1000. You're going to go do it 130 times without replacing. Okay, so if we now do this, we have a data frame here. Just going to show the head of the data frame. So just let's say the first 20, 15 lines is, I think, enough. Oh, sorry. Okay. And we see here, we basically just have the group A here 5 times, and we have some numbers, and then we have the group B and some numbers, and the group C and some numbers, and so on and so on. Okay, good. So what we can now do is to subdivide this data set, and there are different ways how we want to do it. I'm just going to do my way, to be honest. And here, what you might want to do first is to just see how many groups we actually have and save the name of these groups into a specific object. Okay, so we're just going to call it my groups. And the way you can do this is the following. If this column group is a vector, you can just take levels and then df $ group. If this is, however, just a character, for example, you can just use unique. Okay, you use unique here, so you add df $ group. And if we now run my groups, we see here it's exactly these letters, so from A to Z. And if you look into the environment, it says that groups actually is a factor with 26 levels. Okay, and it would work the same way if you would just say here levels df group. Okay, good. So now we have my groups. And now what we're going to do, we're first going to create a folder in your current working directory, which you're just going to call sample datasets. Okay, the way you create a folder is by doing the following. It's literally just there, create, and then you give it a name. Okay, and in this case, it should be in the working directory that we're currently working with. And that's why you do not have to specify the path whatsoever. And I'm just going to call it sample datasets. I think that's how we wanted to call it. Okay, cool. So we do that, and I'm just going to hopefully be able to demonstrate this. So if I go to files here, these are my files now that are in the Peer Club R series folder. Okay, so sample datasets should appear somewhere here at the bottom. Okay, so somewhere here. And if you now run this, haha, we have it somewhere here. Okay, cool. Okay, so it's not alphabetically as I thought it's going to be, but it doesn't matter. But we do see that now we have a new folder here. So you did see that something happened. So this is cool. And this is an empty folder. And now what we are going to do is that we are going to start writing our loop. So what you want to do here is to run this loop for each element of my groups. Okay, so we're just going to call this G in 1 until the last element of group, and we can just take the length of group then here. Okay, and if we just check on this, so let's say 1 and then the length of groups, I'm just going to copy this into the console. We see that these are just numbers from 1 to 26. Okay, so it's going to run this from 1 to 26. Okay, yeah, we can do it like this. There is a different way, but it doesn't matter. Okay, and then the curly braces. And now what I want is to have individual data sets. There are the subset of the original data set, but only for one element of the my groups vector. Okay, so I'm just going to call them df sample. Okay, and what we have to do here is to use subset, and then you can write just df. Okay, and what we are using as the grouping factor is basically the column group, and this should equal the elements of my group at position G. Okay, so it's my groups at position G. Okay, we can demonstrate this. So this is also, again, a way how you're building your for loop. So always check all of these small steps. if we just assign 1 to G. So this is basically the first thing that the for loop is going to do. G is going to be 1. And if we now go into here and run this and check this, it's giving us only the first 5 lines, which have the group A, which is the first element of my group's vector, and then just the corresponding values to that. Okay, so this is exactly what we want. And then we want to write this file. Okay, so write table. And here what you first do is that you first give the name of the object that you want to export or write in this case. So it's just the fsample. And then here you have to add the name of the file. Okay, and we want this name obviously to depend on actual groups. Okay, and you can also just say, okay, it should always be the same name, but it should be in a specific folder. And this is a thing that I'm going to do in the next for loop. So now we're going to just give the file different names. Okay, we're not going to create extra folders, just a different name for each file. And what you can do here is just say something like paste 0. I always use this. Paste 0 compared to paste has a difference that the separator in paste 0 is basically not given. So it's all pasted together. There are no spaces. While if you use paste without the 0, then you have to specify the separator, which can be, it can be dot, it can be comma, it can be basically any character. And if you do not want to have any characters between your strings, then you have to specify the separator as just inverted commas with no space or anything. Okay, so we're just saving some typing if we use paste 0 here. And here, I just want this to be called a dataset for group. And then I'm going to add the name of this group here. So because I know that the paste 0 is not introducing any spaces, I'm going to introduce a space here. So I'm going to introduce space here and do a comma. And then obviously we can use this here. So again, it's just going to be the element of my groups at the position G. We can just copy paste this into the console and we just see that it's going to be A. Okay. And then because this should be a CSV file, I'm going to add a comma here and then .csv. And this is also the reason why we're using paste 0, because obviously you should kind of try not to have a space between the name here and your CSV. It's fine if there are spaces inside, that should all work. But I just don't like having like a string and then a space and then the CSV. Okay. And then because we're writing a table, you have to specify a separator for the table itself. And if you're working on a computer that uses English Excel, then it's just going to be a comma. And we do not want to have the row names printed. So row names should equal F. Okay. So if you now do this, and if you then go to your folder, you will have a file, a CSV file with just this part here. Okay. So we can do this like this. I'm just going to click on sample datasets. And we see here that it's empty. Oh, this is so cool because we're going to see everything that happens. Okay, cool. And one other thing that I'm going to do is, and in this case, it's not that important because this is going to run very fast. I'm just going to say to R that it should, every time it's done here, just write the element in my groups that is currently evaluated so that we know how far R got. This is something that I would definitely recommend you to do if you're not having any output. So in this case, we are going to have these CSV files as output. So you can always go into your folder and just be like, oh, okay, it got to letter, I don't know, it got to the letter D, or it got to the letter Y or something, okay? This is super useful when you're dealing with for loops that might take ages and you just want to know where they're going to finish, just like approximately, you just want to know how far they got. And if you have some output and you can check this output in your folders, you just go there, you check the output, and then you can tell how far your loop got. If, however, you do not have any output, try just implementing some small sentences in between that are going to tell you at which stage you are. So you can either, you can even, let's do it differently. We know that my group is from 1 to 26. You can also basically just cat G, okay? So we're just going to print in the console which loop is now currently running, okay? And that's basically it. So if we now run this, We see here, we have all of these numbers. So it's from 1 to 26, but nothing happened here. Okay. And this is good that this happened, because then you can also see that I make mistakes and I forget to do some things. So what actually happened is that these data files were now saved in the Peer Club R series folder, because I never changed the directory that I'm working with. And I also have not specified anything in the path here to say that it should go into a different folder. So there are different ways how to do that. So we can check it here. And if you go to R series, we do see that we have these data sets here. So these data sets were all created, and we can just click on some of them. I think you can just view the file, and we see here is basically just P and then the value here. So that's all fine. But they were all saved here into this folder because I haven't said R to do differently. Okay, so just use the working directory that was currently set. But I want to have these files in the folder sample datasets. Okay, I'm going to go to this folder again just to demonstrate it. First, before I forget this, I'm just going to add \n here so that we get these numbers into different lines. And then what you can do is either you change your working directory. Sometimes, however, if you're loading the data from one part of the directory and you have to put the data into another part of the directory, it's better not to change the directory directly. That's super cool. It's just better to specify the path. And you can specify the path in different ways. The easiest is actually to just add it to the name of your data file, okay? And in this case, we know that this folder where we want to save the data is the sample data set. So I'm just going to copy paste it into this name here, and you just have to add a slash here, okay? So R will then know it has to first go to the sample datasets folder and then print all of these datasets with the name dataset for group and so on and so on, okay? And now I do hope that this is going to work. So we're just going to run this again, okay? We do not have to change anything here. Just going to run this again. And now we see that. Okay, so this worked perfectly. We see also the numbers here on the side. As I said, in this case, this was also maybe just totally unnecessary because this was running fast anyhow. But if you're doing many multiple steps and you are waiting for hours, then it's cool to just like go back to R and just see at which step you are currently. Okay, but we see it all worked again. We have all these data files here. Okay, so now in the next step, we want to do the quite opposite. So let's say SN here for the section and for loop for files. Just I'm going to call it. There was one thing that I forgot. I might just do it quickly. I'm going to go back here. You're going to have to delete all of these things afterwards. I'm really, really sorry for this. So this is all in one folder. Okay. And this is going to be all in individual folders. We're just going to take this again, copy paste this, and do the following. We're going to stay in the sample dataset folder here. Okay. I'm just quickly going to delete everything that we already have. So you're not going to see this, which is okay. Just going to do it quickly, and you can do it yourself as well if you want. So we're deleting all of these data sets. So now I'm going to delete all of them so that basically the sample data set folder is empty. And I'm also going to delete all these data sets that were created here and not anything else. Okay, so I'm done. So now we see here that it's all gone. But we're still going to stay in this sample data set folder. So now what I want to do is that each time we run this loop, we create an individual folder. And we know already that creating the folders is super easy. We just need to use dir create. However, now we want to also tell it that it should have specific names, okay? Because it should be different folders. So we're just going to use the pay0 again. And we're just going to call it folder and then underscore. And we're just going to add the group here. And I'm also going to show how to do this entire loop differently. We're going to remove this entire part. Okay, so in the first loop, I was going into each element of my groups, and G basically was just a number. In this second loop, G is going to be each element of my groups, not just the index of the element, okay? So G in my groups is just going to be A, B, C, and so on, okay? So we can save also again some code here. So we can just type G here. We do not need my groups G anymore, okay? And this is going to be, as I said, A, B, C, and so on. So just going to create a folder here that is going to have this name, okay? And then we're going to do the same as before, but we're going to remove this again and just call it G, okay? We do not need the entire vector anymore. We're going to do the same here. And then here again, we have to add this new folder now, okay? Because you want each data set to be saved in each separate folder, okay? So we're going to add folder here and then the underscore, but we know that we also have to add the G. So here we have to add the inverted commas first, add the G, and then add this. And obviously, because it's a folder, and then we want to add the data set to it, we need to insert a slash here, okay? So this now has the structure sample data set, okay? By the way, good that we're talking about this. So that R knows that it should create the folders in the sample datasets folders. We can either change the working directory or we just add this here, okay? Good, so this is going to create folder each time. And then in each of these folders, it's going to add the data set for each of these groups, okay? And we're just gonna remove this here because this is not so important. We know that this is all working very fast. And now let's hope that this is going to work. Cool. Okay, so we have folders now. Each folder has the name folder underscore and then the actual group. Okay, so this is now our element G, so A, B, C, D, and so on. And if we click into each of these folders, we have a data set inside. So this one has a data set A. If we go to the folder M, it will have the data set for group M, and so on. Okay, super cool again. Good, and now we can go to the for loop for files. So now we're going to do the opposite. What we now want to have is a data set that is combined out of all of these data sets that are in the different folders. So we have to tell R to go into the sample datasets folder, go to each individual folder, take the data set, save it as an object, reuse it later to combine all objects together. Okay? What you can do here is, for example, the following. We want to know which folders you have within the sample datasets folder, okay? To get that, you can use the function dir, which stands for directory, and basically gives you all the elements within your directory. And I do hope that this is going to work. Just going to call them my folders, and then dir. And we know that currently we are in the Peer Club R series folder, but however, we want to have the sample datasets folder. Okay, and if we now run this, then we get the names of all folders that are within the sample datasets folder. Okay, again, a really cool thing to do. So now we're going to start writing the loop. And again, there are different ways. So we're just going to do it. Let's say, I know that I said you should not use the letter F, but we're just going to use it here. It's going to be fine. And we're going to say F in my folders. So F is going to be each element of the vector my folders, okay? And then we're going to use the curly brackets here. So what we want is to go into each of these individual folders, okay? This is only one step. It goes into one folder, and then take the data set and assign this data set to an object, give it a certain name, doesn't really matter, and then use this object afterwards to combine all these individual data sets together, okay? What can happen is that you have, let's say, different data sets in one folder that can either differ in their name or maybe in their file extension. So in this case, we know that our data set contains the word dataset or like just data as well, and that it has the extension CSV. What we can do then is basically to extract the file name of this data set in this individual folder and then use it afterwards in the read CSV function. I'm going to show how to do this. So we know that these folders, and I'm just going to run them again quickly, have these names here. So we know that when we start with our for loop, F is going to be the first element here. So F is going to get folder A. So just going to put this in here. Okay, so this is again just making sure your for loop is working. So you always have to do these small trials. Okay, so now we have F and it's equal to folder A. So what we now want to do is to get names of all files that are within this folder that we're looking at. Okay, and again, as I showed before, you can just use dir. Okay, so I'm just going to call it all files and just use the dir. And then dir here is going to be this here, so sample datasets, and then the name of the folder. Okay, so I'm going to write here my path is then paste 0 sample datasets, and then just F, because we know that F is already the name of the folder. Okay, if we run this, then we see that my path is sample datasets and then the folder A. And if we just include the my path here and run this, we see that all files now has this one file here. Okay, we can already just use this because we know that there is only this one file, but obviously you want to use it in cases where you have multiple files inside. So the only file that we want now, and we're going to call it my file here, is the one that has the extension CSV. Okay, imagine you would have text, PDF, PNG, TIFF, whatsoever in this folder, but you just want the one file that has a CSV. What you can then do is the following. You take all files that you have, so all files, that's the object where you have the names of all files that are within the folder. And then you take the square brackets and you use the function grepl. In this function, you have to give a pattern that you're looking for. So you're going to look for a certain pattern, which in this case is just .csv. And you have to say where you're looking for it. Okay, so the pattern here is .csv, and the object where we are looking for it is just the all files. So we are going to go into all files, see which of the elements in all files has a file that ends with .csv or that just contains CSV in this case. So this is the pattern here. And if there are different files inside, then this will basically give you a logical vector with true and false. And if you then put that into these square brackets, then you're just going to be indexing all files object by this logical vector. And every time there is a true, it will basically pull out this file. Okay, in this case, just the name of the file. And as I said, obviously here we do not have to do it because we only have one file. But if you have many, then you can just do it like this. And then if you now check it, you have my file here that is also just dataset for group A. Okay, and now we have this. So this is the name of the file, but we now want to extract the file as well. So just the F file is then going to be read CSV. And now here you have to add the name of this file, but it's not going to be enough because you also have to tell R in which folder this file can be found. So we're going to need the my path again, and we're going to need my file again. So we need again paste 0 and then my path. And then obviously because these are folders and a data set, they are separated by a slash. Okay, so we need a slash again in inverted commas. And then just my file. Okay, so this is the actual name. And this already has a CSV inside, so that's all fine. And then as always, you can add this, but you don't have to. The separator of the CSV file is a comma and header equals true. And if we do that, and then look into the df file, we get this. So this is exactly the data set that we saved before into the folder A. And now we're going to keep this. Now we're going to use an if statement. So if, and this is now probably not the best, but so if f equals the first element in the folders, then this df file should be assigned into another object which we're going to call df all. So it should just have all the data sets inside. Okay, I'm going to explain later why I'm doing this like this. And if this is not the case, so if f is not equal to the very first element of my folders, then I'm just going to reassign this, but basically use the df all data frame, add the new file below that. So we know that if this is not the case here, so if f does not equal the first element, this means that we're already in the second folder taking out the second file. Okay, and this file is going to get this name here. So it's going to be, again, the object df file. So taking this file and we're just appending it below the data frame that we just created, and just taking them all together and assigning again into the same object. Okay, and then we need data frame here, and then we need our bind here. Okay, so our bind stands for bind by row. Okay, so just the rows are going to be combined. So like this. So if this is the first data frame, then the second is going to come below that, and we're just going to repeat that. So only the very first time we have a data set. So this is only when we go into the very first folder, we're going to have data file being called df file first, and then we're going to assign it to this other name here, so that we can again use this name without overwriting it. Okay, so then we go to the next folder, take the next file, save it again as a df file, but now we have this df all already. Okay, so this is now the main data frame, the one that we're always going to extend, and this is just the individual file every time. Okay, so whenever we're in the second folder and in the third and in the fourth until the very end, we're going to use our bind to basically append this new data frame below the data frame that you already created, and just repeat that until we have all the files together. Okay, I do hope that this makes sense. Obviously, we could have written this in a different way. If we would have just used f in 1 until the length of my folders, then you could have just said here f equals 1, or f doesn't equal 1. Okay, but we're doing it differently. And obviously, you can also just, instead of if here, you can just use else without the condition. Okay, and when this is the case, you're basically done. You can just use it as it is. What you might want to do is to remove all the objects that you do not need, just to make sure that you're not going to get into a situation where, for example, something didn't work fine, and then my path was not created once again. It just like didn't happen for whatever reason. And then you're going to just keep the old my path, which is not what you want. So just always remove the objects that are repeating here. So the object my path, all files, my file, and the f file are repeating in each of the loops. And to make sure that you are not going to end up using duplicates, so using any of these twice or something, you might just want to remove them. What you should not remove is the df all, because that's the data frame that we're kind of building. Okay, you do not have to do this, because in each for loop, as I said, they are obviously going to be overwritten, but you never know what happens. So maybe you just like think of removing them. So I'm going to remove my path, all files, my file, and the df file. Okay, and then I hope that this should work. And at the end, we should end up with a data frame that is equal to the very first data frame that we had, so the one with 130 observations. And it should be called df all. And that should be everything. We should not have any other new objects here, because we're removing them every time at the end of the loop. Okay, good. I think we are ready now. Let's hope this works. Okay, something didn't work. And let's see. We do have the df here, and df looks perfect. So we have everything inside. Okay, so there is one thing missing here. I can't honestly say why this is the case. And again here. So very interesting. This never happened, but it's cool that we realized it very fast. Haha. Is that f and t are missing, which are usually used also for false and true. And I think that this is a reason why this didn't work out properly. I wasn't aware that this is happening, so maybe just avoid calling your groups F and T, to be honest. Just give them another name. But however, in general, I think that I demonstrated what I wanted to demonstrate. So we see that this is how it would work. It might look a little bit complicated, especially with paths and everything. As I said, if you just change the working directory, it might work easier. On the other hand, here we're basically just like pasting together the folder names and the data file names, okay? And just so you know, obviously, the files are still in their folders, right? So they were just like virtually opened, assigned to an object, and then afterwards combined into an entire data frame, right? And if we, as I said, either look here into the data frame or just run it here, we can also just look at the head again and just look into the first 15 lines. And then we see here that it's exactly what we had before. We can just also run the actual file that we had from before. And we see that it's, so this is the DDF. I've just run it twice, sorry. And we see that it's exactly the same. So these are exactly the same. Okay. So yeah, so this I think is already pretty much enough. It's been now a much longer video than I thought, but as I said, I was so super excited about this. And I do hope that this is helpful. We can do much more with loops. So you can use the for loops for many different things. I've used it for bootstrapping in my very first paper, something that I might bring up as an example in some of the other videos. Or for example, I was running some models where I had to specify different parameters that were in a certain range. So obviously for each of these parameters, I had to run an individual model. And I had, let's say, 3 different parameters, all of them in different ranges. So I had to account for all combinations. And these are all the things that you can just do with a for loop. So basically, you would end up having 3 for loops then. So you have a for loop for each of these parameters. They're like within each other, not after each other, just like within each other. So you have the most inner loop, then the second loop, and then the most outer loop, basically. And you run all of this. You can save everything. You can have a data set afterwards with all the results. And this is something that you can write once and just let it run. And you can go outside, have a walk, come a few hours later, and everything's going to be done for you. Okay, no copy pasting. This is the most awful thing in scripts, is basically when people just like copy paste, copy paste, copy paste. It's boring. It's like you lose track because you do not see what you've done already, what not, if you maybe missed something. And also it's for someone who is looking at your code, very unexciting, because someone is going to go through the code and be like, okay, so this is the same stuff repeating like, I don't know, 50 times, just very, very long code. No sense to do it like this. And until they find something that is actually different, they're probably going to like lose any hope for the script. So really, really try to use these loops as often as you can, or any other alternative. As I said, if you feel more comfortable with using map or with using the tapply, sapply, lapply, something like this, and know that there are people who would much rather work with that. Again, it depends on the data set that you're working with. It depends on how much control you want to have over it. It depends on how many small bits and pieces you want to add to it. So as I said, you have the control over the for loops. You have the freedom over the for loops because you can basically add anything that you want. And they're just super fun. Okay, so I hope that you enjoyed this. Sorry for it being too long, but I just thought that this is the most basic that I could show that is already preparing you for whatever you're going to do next. And yeah, tell me if you have any questions or any feedback. Thanks for listening.